Hello, everyone. Welcome to this interview with Professor Tim Spiller. Professor Spiller works in the Department of Physics at the University of York and is a professor in quantum information technologies, as well as being the director of the York Center for Quantum Technologies. Professor Spiller was my primary PhD advisor at the University of Leeds, and I'm delighted that he's joining me to discuss the exciting and emerging field of quantum technologies, along with how you can learn more about this and the many interesting careers in the field. So welcome, Tim.
Thanks very much, Suva, and hello, everybody.
So, Tim, can you tell us when and how you first became interested in physics?
Yeah, so, all right. When I was a little kid, I was interested in two sorts of things: mathematical problems and fiddling with stuff. So building things in Lego or Meccano or whatever. So I went off to school kind of with those interests already there. And at school, I was always interested in science. And I'm not a mathematician. And I think I even knew this then. I don't think like a math. I like to use mathematics as a tool to do stuff rather than actually just do it for its own sake. And I think I knew that already. So I'm good at mathematics. I can use it, but I was never interested. So, I gravitated towards science. And well, let me use Rutherford's pompous quote that all science is physics or stamp collecting, right? So well, the chemists got their own back because his Nobel Prize was in chemistry, not physics. But I think the reasoning behind his flippant comment was that certainly 50 years ago, when I was learning physics, was still then the most quantitative of the sciences. So if you wanted equations to describe things and you wanted to use mathematics, then physics was the subject for you. So I kind of, by default, I think I ended up as a physicist rather than any other kind of scientist, because I like using mathematics to describe things.
And was there a particular area of physics that grabbed your attention and really motivated you to study physics at uni?
Well, when I was at school, and certainly in the sixth form as well, I really liked mechanics, and you didn't do much to do with quantum stuff at that level. So I kind of mean classical mechanics by that. But you were given hints that there was something beyond just classical mechanics, and I certainly thought classical mechanics was really nice and elegant and interesting. So the fact that there was something that you could learn that went beyond that was certainly really interesting. And I was certainly, particle physics was also kind of the buzz subject at the time. So I made sure I did all of those options when I went off to university. So that was one of the things that also drew me into physics, I think.
That's interesting to hear that you were really into classical mechanics, and that's what motivated you, because quite often students these days will find classical mechanics a bit of a bore because, of all the other cool and exciting stuff around in contemporary physics,
Yeah, but 50 years ago, I don't know. I think it's very elegant, and you just began to get one or two hints about the more elegant ways of doing classical mechanics when you were in the sixth form, and so I think that was enough of a magnet for me to want to learn more.
Yeah, I agree. And actually, as I tried explaining once to a tutee of mine, classical mechanics is an evolving subject even today. There's been plenty of surprises in it, over the last 30 to 50 years, and it's still people doing research in it and things like chaos theory, dynamical systems. So it's very interesting area. So yeah, you mentioned particle physics. That was what you did your PhD in. Specifically, you investigated theoretically how heavy quarks would decay into up and down quarks, which are the quarks that make up protons and neutrons. Today, of course, your areas of research are quite different. In simple terms, could you tell us a bit about how and why your research interests have changed over the years?
Yeah, I don't want this to kind of put people off, but in particle physics, think back. This was the early 1980s, so the internet didn't exist, and you got papers on the archive through the post each week. So there was nothing electronic going on, and it was actually quite hard to get hold of data. So, as a theoretical particle physics physicist, you couldn't just ring up CERN and say, "Oh, could you by any chance measure this for me? Because I quite like to see the numbers on that." You had to claw data out of papers because, even in those days, particle physics was big science. So the experiments were planned many years in advance. They were big teams and so on. So it was quite hard to have an element of flexibility in that. So I really enjoyed doing the work, but I found it quite hard to interface what I was doing with real data.
Mm-hmm.
And so I think you either had to join a big team, which, in principle, I could have done after my PhD, or if you wanted a kind of faster turnaround, you needed to work with experimentalists in other fields. And so I don't think there's any way I was going to not do quantum physics, but I wanted to find areas in quantum physics that I could move into where I could collaborate with people and get a more rapid turnaround on experimental results and that. So I started moving into working on quantum effects in actually superconducting systems. So, this was the late 1980s and early 1990s. And I was working on things that are now called superconducting qubits, but they weren't then. So we were looking at quantum effects, just about being able to see some quantum effects in superconducting circuits back then. And now these are the elements that are in Google's quantum computer or IBM's quantum computer. So, but it was nice because I was working with an experimental team, and you could just walk down the corridor and have a chat with them and say, well, could you do this instead? And maybe a week later, we'd be doing a different experiment and measuring different stuff. And I liked that turnaround. Mm-hmm. So, yeah, as I say, I wasn't going to move away from quantum physics because that's what I'm really interested in. But I preferred the short turnaround and interaction with an experimental team that was actually in the same building rather than one that was somewhere else in the world.
Mm-hmm. So you're one of those theorists who wants their work to be grounded in the real world, the real messy world of experiments, right?
yeah, do it in the right number of dimensions and etc. But no, I think I mean, in the end, physics is an experimental subject, right? So, we need all the mathematical stuff and all the theories to describe it. But if none of it can be measured or verified, then we don't actually know. It's all then just abstract theory. So I like theoretical physics to link to what can be measured.
Right. So, as I mentioned in the intro, you're the director of the York Centre for Quantum Technologies, and the University of York's is a key member of the UK National Quantum Technologies Programme, which funds the Quantum Communications Hub. Could you tell us briefly what's meant by quantum communications, why it's scientifically interesting and important for society, and also the nature of the Quantum Communications Hub and its activities?
Yes, there's quite a few questions there. So let me unpick it bit by bit. So new quantum technologies in general, there are various fundamental features in quantum physics, and the three that kind of stand out, I think, are superposition and entanglement and the irreversibility of quantum measurement. So that's the unavoidable disturbance when you measure quantum things. Now those three features, at least one of those, but it could be more than one, plays center stage in one of the various quantum technology sectors. So in quantum computing, it's really superposition and entanglement, and in quantum communications, it's the irreversibility of measurement. But the whole field of quantum technologies now are these new technologies where one of those fundamental, and some people say strange, in the sense that they're not everyday things that occur in conventional classical physics. They're new things. These phenomena play center stage in these new technologies, and so in the area of quantum communications, then the important feature that you get is the potential for security, and that security in communication or at least communication applications of some sort comes from the third feature I mentioned, which is this irreversibility of quantum measurement. So the idea in quantum communications is that the scenario is always Alice talking to Bob, right? So if Alice sends quantum states of something to Bob, and these quantum states will in general for communications be states of light, and they might be going down an optical fiber, or they might actually be propagating through free space. But either way, if Alice sends quantum states of light to Bob, then if somebody has a look halfway along and intercepts some of those, then they cannot avoid disturbing them, even if they prepare and send on exactly what they've just detected. Alice and Bob can work out if someone's been having a cheeky look. And if the conclusion is that they haven't, so Alice and Bob can conclude that the stuff that Alice has distributed to Bob, say, is uncorrupted by someone else having a look, then they can, Bob can measure the states when he receives them. And there is a protocol then by which Alice and Bob can agree a key, a shared mathematical key. So this is now ordinary information. And that key can be used for encryption. It could be used if Alice is a user and Bob is the bank, then Alice could use the key as a PIN number, a rolling PIN number. So there are all sorts of security applications. But once they've agreed that they have secure keys shared, then there's plenty of things they can do with those. So the offer of quantum communications is a potential way to do security. People say based on the laws of physics. It's this disturbance that is always introduced with quantum things when you measure them that basically gives you the security. So that's the basic idea. Now, the quantum community, you mentioned the UK National Quantum Technologies Programme. So that programme set up a number of big activities. In fact, there are 4 hubs going, and now there's also a National Quantum Computing Centre. So these big activities have been set up not to do more quantum research, but to actually take the quantum research and apply it into turning it into real usable technologies. And so, the quantum research is still funded in the fundamental research program in the UK. And most of the people who participate in the National Technology Program are also part of the fundamental research program. They will be doing stuff there as well. But the idea is that when the hubs were established, they were set up so that they would take the quantum research results that were already known, and they would push them as far as possible towards working technologies. So in the hub, we've been pursuing quite a number of different routes for turning quantum science, if you like, into working quantum technology.
Okay, so perhaps you could give, in simple terms, or describe a research highlight to have emerged from the Quantum Communications Hub?
Yeah, I'm going to be cheeky and give you a few, I think. So
okay, that's fine.
It's like picking your favorite children.
Yeah.
Right? You can't do it. So, as I said, the focus is on turning the science into technology, and part of the push towards technology is clearly towards miniaturization and low size, weight, and power. So in terms of the actual hardware, there's been a lot of activity making stuff smaller, putting it on chip, and indeed even out of our hub at the University of Bristol, there's now a startup company has emerged doing exactly that. So on the hardware side, we've focused on making things smaller. But in terms of what we've achieved, I mean, clearly, I mentioned you could do stuff through free space or fiber. Well, we already do conventional communications an awful lot through fiber, and these days fiber networks, are very extensive, and actually now they're moving to the stage. So modern fiber networks are reconfigured within a software layer, if you like, that sits above the hardware, and we've started introducing that aspect, the reconfigurability, into quantum communications within fiber as well. So we've certainly shown that the first steps towards that. We've also done work with entanglement. So I mentioned entanglement before. That's where things that are well separated, quantum things, can be correlated more strongly than they can by any conventional means. And those correlations can also be used to establish shared keys and so on. And so we've done networking using fiber to distribute entanglement, both from the perspective of distributing it between, I'll say multiple parties. It's got up to 4 at the minute. So you can distribute entanglement and actually share a key between 4 users at the same time, rather than just Alice and Bob. You know, you can add a couple more. So that's been done at Heriot-Watt University, and also in Bristol. They've established a kind of mesh network between many users and shared two-way entanglement between all parties within that network. So these, if you like, are the baby steps, the first steps towards what people say in the future would be a quantum version of the internet. I think there's an awful long way to go on that, but you know, the first steps towards that are being shown in principle. There's one final thing I'll mention, because I've spoken about fiber stuff. If you want to go very long distances, intercontinental and so on, then clearly the use of satellites is going to be very helpful. And so we plan, so I won't claim we've done this yet, but it's in our plan for future work that we will be doing a satellite to ground quantum communications demonstration. So there have already been examples of that done elsewhere in the world. So the Chinese have already put up a satellite and shown that this can be done in principle. And so we want to look at that from the perspective of doing it from a small satellite to the ground. So that's on our agenda for doing in the next few years.
Ah, that's very exciting. So New Scientist Live Manchester Science Festival will be taking place in Manchester Central and online between the 12th and 14th of March this year, 2022. So wherever you are in the world, you can experience the New Scientist Live Festival. I'll leave a link for this in the video description. Visitors will be able to experience the Quantum City exhibition. What is Quantum City about, and what can visitors expect to find at the Quantum City stand? Will you be there?
I think we will have a presence there. So we're certainly contributing to. So first of all, Quantum City is kind of the outreach or the public engagement arm of the UK national program. So I said there were various hubs and that. So I run the one for quantum communications, but there are ones on imaging, sensing, and computing as well. And there's also contributions to Quantum City from the National Physical Laboratory and also from the Quantum Science and Technology Institute at UCL. So as I say, Quantum City is the outreach and public-facing part of the UK national program. So it's designed to provide demos and exhibits at the appropriate level for outreach, and you know, one or more of the hubs will generally go with some Quantum City stuff to science fairs or whatever. So we've got a history of doing that, and New Scientist Live is clearly a very big and really exciting opportunity for doing this. So we'll be doing quite a bit, and as I understand it, there will be a number of exhibits there where people can actually engage with that. So very briefly, I mentioned there'll be one that certainly focuses on quantum communications with light. So, you know, kind of set up with Alice and Bob and some eavesdropping in the middle, so you can get the gist and understand for real how quantum comms works. There's also one to do with some of the quantum imaging stuff that's done. It basically requires detection of photons right down at the single photon level, and you know, there are very good detectors that do that now. Actually, the human eye is not bad. You know, it probably can't detect one photon, but it can detect a modest number. So I think there's an exhibit where you can basically get to grips with pretty much single photon imaging and understand how that works. There's also another exhibit showing interference of photons. So I mentioned superposition. Well, if you have superposed states, then the different amplitudes can interfere with each other, and interference with light is something that you can do with classical waves, and it translates down into the quantum level as well. So I think interference with light is something where people can get a good understanding of quantum stuff, and so there will be an exhibit on quantum interference. Another very interesting application on down at the atomic level is timing. So the most accurate clocks that operate in the world are based on single atoms vibrating between a couple of their levels, and so there will be an exhibit from the National Physical Laboratory about atomic clocks, and the final one is actually a very practical example of a quantum technology that's now emerging, and that's quantum brain imaging, or quantum enabled brain imaging. So there's actually a helmet that can be worn by someone which has a load of little quantum sensors in it, and you can actually start to image the fields of the brain with these sensors, and in the end this could be the way forward on better diagnosis for some of the brain diseases that exist, so Alzheimer's, Parkinson's and things like that. If you can see early signatures of that by imaging the behavior of people's brains, then maybe you can learn more about how those develop and come up with ways. So that's come out of the Sensing and Imaging Hub, and it's work by the University of Nottingham that's been done over a number of years, but it's now very impressive. I've seen it at a Royal Society exhibit before. It's really very good. So there's a whole range of things that are going to be shown at Quantum City at New Scientist Live. So I would encourage people to participate. As you say, I think there's stuff on the web, even if people can't attend in person.
Yeah, I think the main New Scientist Live talks will be presented online. So yeah, I'm not sure if people will be able to, visit the Quantum City stand virtually. I don't know if you know about that. Probably, possibly not.
I don't know, but I think there will be links that you can put up that will tell people what can be seen.
Yeah, I will do. Yeah. So the current A-level physics syllabi touch on some introductory quantum physics concepts. I mean, you mentioned interference, but so other things such as photons and wave-particle duality. Do you think the A-level physics quantum components needs updating in order to train and inspire the next generation of quantum scientists and engineers? So could concepts such as qubits, quantum bits, which underlie quantum technology, should they be introduced? Or is it still okay for this stuff to be first met at university?
I think it's okay for it to be met at university. So I don't want people who miss out at sixth form or lower to think they've already missed the boat. So I think that's an important point to make. But the short answer is yes. I think if you can motivate and engage people earlier, then absolutely we should. But another advertisement, we've mentioned Quantum City, and there's clearly material on the Quantum City website that people can access when they're still at school. But I would also say, because I do agree that there should be additional stuff at A-level, then the national program also has what's called the Quantum Ambassadors scheme running, and so our hub actually set this up for the national program. So we run it for the benefit of the whole national program. But what the Quantum Ambassadors scheme has done over the last few years is it's developed a load of material that discusses exactly the sort of things you just mentioned. Simple examples on qubits and how they can be manipulated and so on, that kind of thing. So it's introductory material that's a stepping stone towards doing proper quantum physics. And so the material exists, and people have also been trained to go in and help teachers present this material. So these are the quantum ambassadors. And so that's been pushed out into quite a number of schools already. And it's actually, it's very convenient for our hub because the National STEM Learning Centre happens to be based at the University of York as well. So we've been working directly with them on this material, and I think you're going to give a link to that as well. So if people wish to follow up on that and start to get access to the material and so on, then there will be a route to do that through the National STEM Learning Centre. But no, in general, I would agree that it would be good to have more of this stuff at A-level, but I don't want to put people off and have them think that if they don't engage with it at A-level, it's too late. It isn't. You know, you can pick it up at university, but it's nice to get more motivation, I think, by working on it earlier at school.
Yeah, I mean, I don't know if you noticed, but polarization, for example, classical wave polarization is taught anyway in most A-level physics syllabi. So it'd be kind of nice to talk about polarization states of photons, right? There's clearly.
Yeah, I think that is actually explicitly part of the material on the quantum ambassadors site. You know, I gave some input into that, and so it was developed by teachers rather than people like me. But we gave input, if you like, to make sure that it was. And I agree, photon polarization is an excellent way to talk about it, because polarization of light is something we can all relate to.
So yeah, whether you're a student or an educator and you're interested in quantum technologies outreach coming to your classroom, you can find out more about the Quantum Ambassador Scheme that Tim has mentioned via the link I'll leave in the description. So what advice would you give to someone who likes physics, may have heard about the promise of emerging quantum technologies, but still doesn't know if studying physics is the right thing for them? They might be unsure about their career path or prospects after university.
Well, I guess as a physicist, I'm going to plug a physics degree in the sense that I think at the minute you certainly need, if you want to work in quantum technology areas, you need degree level stuff, and if you want to do really specialist things, then maybe via a doctorate as well. But I think a physics degree is still a very good starting place for that. It's true now that there are, so quantum technology is not about physics, right? It's about engineering. There's bits of chemistry that come in now, certainly mathematics, computer science. So there are quite a number of undergraduate degrees that will open up access then towards work in quantum technology. So you know, it's not exclusively physics, and I don't want to give that impression. But at the same time, I would say a straight physics degree is still a very good grounding, in that you'll learn enough quantum stuff, you'll learn enough basics about all other aspects of physics, so you can put it together in an appropriate way. You certainly now will get some quantum stuff in some computer science degrees or engineering and so on. So there are other routes, but I think certainly a degree in one of those subjects gives you an opportunity. But in terms of a physics degree, there's lots of things one can do with a physics degree. So just a plug for the UK Institute of Physics, you know, their website gives a list of things I think still that you can do with a physics degree, and some of them you might not guess to begin with, but it's quite a versatile degree, because it shows that you're capable of problem solving, you're numerate, and you can think on your feet. And most degrees in all subjects these days teach all the soft skills as well. So I think it's a very good place to start.
And finally, what's the most inspiring thing about working in the field of quantum technologies? Or maybe there's not one thing you can single out.
I'm going to give you two answers, actually, because I mean, certainly it's now seeing the technology emerge, because it was the late 1970s when I was an undergraduate, and so studying physics then, you were taught about superposition and entanglement and measurement, but nobody told you those things would be in technologies in the future, because it wasn't known.
Right.
So you learnt about that stuff, and it was absolutely fascinating, but it seemed to be the academic underpinnings of quantum physics, and that was it. You know, everyday use of quantum physics wasn't going to involve that kind of stuff. And now I've watched the whole thing develop from there through my career. And so the fact that now real technologies exist, you know, you can pretty much buy them, or you can certainly see them in people's labs. that actually use these fundamental features of quantum physics, I just think is amazing. That's and it's great to have watched that emerge over my my 40 years of career. But the one other thing now that I also think is fascinating is that the quantum technologies, or certainly aspects of them, are now feeding back into fundamental physics and giving us new instruments or new ways of actually learning more about fundamental physics. So, maybe there can be better detectors of dark matter or things beyond the standard model and so on. The LIGO gravitational wave detector has now used squeeze states of light in order to make it more sensitive. So I think the quantum technology work is great, and I feel really inspired by doing that. But it's also really good now to see that feeding back and providing instruments that are not only just for medical use or whatever, but also fundamental science use. So I think it will trigger off new discoveries in fundamental science as well. So you put those two together, and I think it's really exciting.
Yeah, no, that is certainly very inspiring. Thanks again, Tim, for joining me and sharing your knowledge and insights about quantum technologies. To our viewers, I'll leave links for many of the things we touched on in the interview so you can learn more about them if you want to. Thanks for listening. Don't forget to like and subscribe if you haven't already, and leave a comment. It'd be great to hear from you. So take care, and I hope to see you soon. Bye.
Thanks very much. Bye, everyone.